Hi everyone, thanks for coming. Today we have Isaiah Andrews. He's a professor in the econ department at MIT, and he'll be presenting work entitled Identification of and Correction for Publication Bias, which is joint with Max Kazi, who's here in the econ department.
Great. Thank you all very much for having me. Thank you for the invitation, and I'm really excited to get all your comments. This is a relatively recent paper. We just posted a working paper a couple weeks ago, so I'm extremely eager for feedback. So the background for this project is that replicability is at least supposed to be a fundamental requirement of science. Right? In particular, we want different researchers studying the same question to be able to reach the same conclusions. And we have methodological conventions which are intended to ensure this. Right? For example, the use of randomized experiments. Despite these often quite restrictive methodological conventions, however, replicability frequently appears to fail in practice. By the way, let me know if the volume is too high, too low. It's weird hearing an echo. Okay, cool. So such replicability failures have recently been documented, for example, in experimental economics, experimental psychology, medicine, cell biology, and neuroscience, just to name a few examples. Now, there are many potential reasons why, right, when we go back and try to reproduce results from the existing literature, we might not be able to. And one possible explanation, or one possible contributing factor, is selective publication of results. And when we talk about selective publication here, we have in mind both selectivity due to researcher decisions of which of their empirical results to write up and submit to journals, and journal decisions about which of the submissions to publish. For example, you could think about there being selection on statistically significant effects, confirmation of prior beliefs, or conversely, novelty. Whatever the reason, though, if we have such selectivity in which empirical results get published, it can lead to biases in conventional estimators, and conventional inference procedures may fail to control size or coverage. So against this backdrop, in this paper we make three main contributions. The first is to show nonparametric identification of selectivity in the publication process, and in particular of the conditional probability of publication for a result conditional on whatever the empirical result is, using two different strategies suitable for different contexts. The first strategy focuses on replication studies. So these are cases where we can take the same experimental protocol as the original study and apply it to a new random sample drawn from the same underlying population. And the idea here is that absent selectivity, the original and replication estimate should be symmetrically distributed, in the sense that if I flip which I label the original and which I label the replication, the joint distribution should be unchanged. Deviations from that symmetry we show are then enough to identify the conditional publication probability. For many contexts, though, we can't run replication studies, for example, if we're using observational data. And in such cases, we propose an alternative approach, which we call the meta-study approach. Here, the idea is that under a suitable independence assumption, the distribution of estimates for small sample sizes, or imprecise studies, should just be a noised-up version of the distribution for large sample sizes or more precise studies. Again, using deviations from that prediction will allow us to identify the conditional publication probability. Now, once we identify the form of selectivity, we can develop corrected inference procedures. And in particular, we propose median unbiased estimators that correct for selectivity in the publication process, as well as confidence sets with correct coverage. I'm not going to talk about it today, but in the paper we also develop results which allow for nuisance parameters in multiple dimensions of selection, as well as results on Bayesian inference correcting for the effect of selection. Finally, we take these theoretical results and apply them in four settings. The first using data from a recent large-scale replication study in economics, the second to data from a large-scale replication study in experimental psychology, the third to the economics literature on the effects of minimum wages on employment, and the fourth to the literature on the effects of deworming on child body weight in developing countries. So just a quick preview of where I'll go in the rest of the talk. I'll start by setting up the model that we use to think about these issues for the rest of the talk. I'll then discuss our main identification results, discuss bias-corrected inference, turn to the applications, and conclude. But before I launch into that, are there any questions at this stage? Okay, great. So let me get started with the setup. So I'll describe the setup in words and then give you the formal mathematical setup that we think about. So in words, we assume there's a population of latent studies, that is, studies which may or may not ultimately be published, indexed by I. The true parameter value in study I is theta I star, where here we'll use star to denote variables in this population of latent studies. Theta I star is going to be assumed to be drawn from some population, so we'll be taking an empirical based perspective here. And an important point is we allow the possibility that different studies in our sample may recover different true parameter values. Right? So we don't have to assume that all the studies in our sample are in fact estimating the same parameter value, although that's of course nested as a special case. Each study then reports findings xi star, where we'll assume that the distribution of xi star, conditional on the true effect theta I star, is known. Right? So the leading case to think about here would be, we've a normal estimate xi star, which is centered at theta I star. Now, each study in this population of latent studies may or may not be published, and this publication decision will be determined by choices by both the researcher and the journal. We're not going to try and disentangle these two, and without additional data, we actually couldn't disentangle them anyway. The upshot, though, is that the probability of publication, which we'll denote by a dummy di equal 1, conditional on the estimates xi star and the true effect theta I star, will be assumed to be some function of the estimates xi star. Right? So this says that conditional on the results, there's no additional dependence of the publication probability on the true effect in each latent study.
Why do we know the distribution of xi star given theta I star?
So the canonical, sort of the leading example and the one that'll be the relevant one in all of our applications is xi star will be a z statistic, right? And so so the z statistic, conditional on whatever the true effect is in a given setting, the z statistic is approximately normal and centered at something that depends on the true effect.
Why?
What? Basically based on the same asymptotic approximations we use for inference, right? That justifies this approximate normal distribution for the z statistic.
Okay, so we're assuming it's we're assuming the really big sample size.
Exactly, yeah. So essentially, right, the justification for that is assuming basically large sample sizes in each of the underlying studies. Now, in the applications where we use it, that's the same assumption that's being used to justify inference in sort of the underlying studies and the replications. So
I wonder whether you could put one other sort of realistic thing in there.
yeah,
I mean, I understand the point of asymptotics is it's some way of approximating the thing you need, which is
Yeah.
the distribution. So, okay.
yeah,
But if you think about every study, no one ever has a sample larger than they need, because if they do, they look in subsamples and subsamples and subsamples.
yeah,
And so basically, it's always the case that our t-statistics are 2. Like always.
Yeah.
I mean that's not a mystery, right? Like
Yeah.
we're always looking. We're turning the telescope up to 10, we're standing up on our toes, and we're squinting as hard as we can. That's what we always do. So
Yeah.
t-statistics are basically always 2. I just wonder whether that could be part of the model at some point.
So, I mean, in some sense, I think there's a sense in which sort of the model that we're going to think about here is basically where, a study, basically researchers see a study, and then each researchers see a result. Like our baseline model here is researchers see a result, and then each result gets published or not, sort of on its own merits, right? Which is actually already inconsistent with the story that you're telling, which I completely agree. I think the story you're telling is very realistic, right? In some sense, maybe you prefer this story if you think of this as a story for the headline results in a given paper, or sort of the main effect estimate in a given paper before we break things out by subgroups and stratified by this and controlled by this. Or does that make sense?
Well, I mean, you're hypothesizing about what's in people's file drawers, and so you have to have some model.
Right. Yeah.
I'm just saying you might at some point want to adjust the model and see whether it comes out differently.
No, absolutely. I mean, I think that's a great point. And in the paper, we actually have some additional results which don't entirely relax things along that margin, but can speak at least to basically which allow for a more general model of how the selection is taking place. And by virtue of that, can at least do a better job of sort of speaking to this issue of what if people see a bunch of results and then pick the best one, right? Or I see the result and then I subdivide and I pick the best of the two, or I sort of iterate on this process. Yeah, so I think that's a great concern. It's sort of the results I'm going to talk about today don't fully speak to that, though. Any other questions at this stage? Great. So just to take the model I just described in words and describe it formally, we assume that in the population of latent studies, there's a set of latent variables, DI, the publication decision, the result or estimate xi star, and the true effect theta I star, which we'll take to be jointly IID across latent studies I. The true effect theta I star is drawn from some distribution mu. Conditional on theta I star, xi star then follows some distribution f of x star conditional on theta star. Finally, conditional on x star and theta star, the study is published with probability p of xi star. We then assume that we observe only the published studies, right? So basically we have some notation here for ij where the function of this is just to collapse the sample down to the studies with di equals 1. That is, the studies with the publication dummy equal to 1. We then denote the true effect in the jth published study by theta j, and the estimate in the jth published study by xj. So to make all this a little more concrete, let's talk about a slightly more specific model, right, or specific setting. So think about a journal that receives a stream of studies, I equals 1, 2, and so on. Each of these studies reports an experimental estimate, xi star, of a treatment effect theta I star, where the distribution of theta I star across this population of latent studies is mu. Suppose that conditional on theta I star, xi star is normally distributed with mean theta I star and variance 1. Right, so this corresponds to the case where the xi stars are z statistics, right? And we're willing to buy the assumption that z statistics are approximately normally distributed conditional on results. We then think about a simple model for the publication probability, where results which are statistically insignificant at the 5% level, that is, where a two-sided z-test of the null hypothesis of 0 doesn't reject, are published with probability 10%, while significant results are published with probability 1. Right, finally, as before, published studies report estimates xj of the treatment effects theta j. So in this setting, we can calculate, for example, the median bias and coverage of published estimates and confidence sets. So on the left panel here, on the horizontal axis, I have the true effect theta. And on the vertical axis, I have the median bias of published studies. Right, so for example, what this figure says is that under the scenario I just laid out, right, the median published study in which the true effect is 1 has an estimate equal to about 2.3. Right, we see that the median bias is 0 at 0, right, which makes sense since the setup I just gave you is symmetric around 0. Right, the median bias then increases sharply and then gradually declines till the point where it vanishes once the true effect is out at about 5. Right, the reason it vanishes out here is once theta is about 5, the probability of observing a draw anywhere close to the cutoff for statistical significance is very low, and so sort of the selection doesn't matter once we're out here. Likewise, we can calculate the true coverage of published confidence sets, where here we're thinking about the usual point estimate plus minus 1.96 standard error confidence sets. And we see that when the true effect is 0, that coverage can be as low as 65%. It actually comes up and above the nominal 95% coverage for an interval here, and then drops back and is equal to the nominal, approximately equal to the nominal coverage once we're out at about 5. So this makes sense? Great.
So in this example,
Yep.
the theta is the test statistic, right? Not the effect size.
Sorry, no, so theta is the it's the mean of the z statistic.
So the z statistic.
Exactly.
So as the sample size is changing, if the sample size goes up, so will the
Right.
theta.
So sort of if you thought about, I'm thinking about a particular treatment that has a particular effect size, and I think about driving the sample size off to infinity, right? Then as long as that's not 0, right, then the theta that we're thinking about here would get larger, right? In some
Why
sense,
does theta get larger? I thought it was a parameter value.
so theta is the true effect, right? So so theta, right, in this example, theta is the mean of the z statistic.
Which is going to change as the sample size gets larger.
Why?
You're saying if as the sample size for the underlying study. I mean, it depends on how are you thinking about making the sample
And
size
so
larger.
I had initially been thinking of theta as the actual effect size,
Mhm,
irrespective of how large the study is. You're
Yeah.
saying that there's a group of studies out there with varying effects, varying sample sizes, and that's embedded in the distribution of theta.
That could they could have varying sample sizes, and that would be embedded in the distribution of theta. They could have the same sample size and different effect sizes, right? Which would also be embedded in the distribution of
Wait,
theta.
I don't know what, I thought theta was a different effect size for each study.
Yes, it is.
So why would it increase with the sample size?
Oh, so as I understood the question, I thought it was just basically if you ask, I have a particular treatment in mind, right? And I think this particular treatment has a particular true effect size. I think it decreases mortality by 1%, say, right? And then I want to know what is the theta for that study, right? Well, the theta for the study on that would depend on what your sample size is, because here I'm defining theta as the mean for the z statistic.
The z statistic is an estimator of
Yes.
theta.
It's a scaled estimator of theta, right? It's an estimator of theta divided by the standard deviation, but yes.
Oh, that's what you're talking
Yeah.
about.
Yeah.
Oh, I see, okay.
But-
I misunderstood.
But yeah, I mean, all that we're doing here is we're just sort of collapsing things down to the z statistic and assuming a publication decision based on statistical significance.
But if you allow different studies to have different sample sizes, earlier you said the theta follows a common common prior distribution, but that supposedly doesn't depend on sample size.
Because implicitly what we're doing, right, is we're saying, right, there's some joint distribution of true effects and sample sizes in the population, right? That implies some, as we define theta here, that implies some marginal distribution of thetas, right? The mu is that implied marginal distribution of thetas, right? So implicitly you can think of this distribution mu as it's collapsing over the joint distribution of true effects and sample sizes in the population of latent studies.
But let's say I'm a dictator and I say no study will be done with a sample size less than 10,000 from now on. That's going to completely alter your distribution of
Exactly.
theta. So it's not the it's not the actual effect sizes out there. It is conditioning on the
Yeah.
sample sizes that the investigators choose to make.
Yeah.
So
In this, in this
and is that
example.
going to be the case throughout the presentation?
Depending, so basically, right, I mean, in some sense, you could think of doing this analysis, right, implicitly, you could think of doing our analysis conditional on whatever, if there's some set of variables you want to condition on and then do the analysis, then that's sort of completely fine from our perspective. So one variable you could condition on is condition on the sample size, right, and say conditional on the samples, I want to think of this distribution mu as the distribution conditional on studies that have sample size 1,000, 10,000 or more. Right, so that's totally fine. We will think about a model later where the theta is the distribution, the mu will correspond to the distribution of the unscaled effects, and then we'll also have a distribution for the standard errors. So we're sort of flexible about which way.
That seems,
So theta
Which way
is
you wanna
the
think
mean
about it.
of a set of unbiased estimators.
So in this example, and actually in most of our examples, we're going to say, yes, we're going to think of the latent sort of unpublished estimates as unbiased. Yeah, definitely. In principle, there's nothing in our setup that says that has to be the case, right? I mean, our sort of baseline result, some of our results later will be using a normality assumption, so then it will have to be the case. Our baseline model here just says it's some distribution, but in all the applications, we'll be using the normality assumption, so in that case, yes. Any other questions here? Great. Okay. So the main point I want to make with this slide is just that, right, we can see that in this setting, right, this selective publication can induce both substantial bias in estimates and substantial distortions in published confidence sets. So the next thing I want to talk about are our identification results. So in the model I just set up, right, a key unknown object, at least unknown to us as people trying to read the published literature, is the publication probability P. And so again, this is the conditional probability of publication as a function of a study's results. And we propose two approaches to identifying this. The first focuses on settings where we have data from replication experiments. Right? The idea here is that we'll have a replication estimate XR for the same parameter value theta as was used to as generated the original estimate. Right? So in some sense, this is saying this corresponds to the case where we can take the experimental protocol, apply it to a new sample from the same population, which should allow us to estimate the same parameter. The key assumption here will be that selectivity operates only on the original estimate X and not on the replication estimate XR. Right? So the scenarios we'll be applying this in later basically correspond to large-scale replication studies. Right? In one case, the replication team replicated 18 published studies, in another case 100 published studies, where we think it's a reasonable assumption to think that we would have seen these results, or these results would have gotten written up regardless of what they had found in these replications. Right? This would be more problematic if you sort of thought of one-off replications, where someone only tried to replicate this study because they thought it was sort of a very strange initial result, and then if they hadn't contradicted the original result, they wouldn't have published it.
But that's the actual story, though.
So for the applications we use, they selected basically they tried to pick a representative set of studies published in particular journals over particular years. In the economics case, they had all experimental economics papers published in 2 journals over a 3-year period. In the psychology replication case, they didn't quite get complete coverage, right? So there, I think there's
exactly what we were describing earlier. They picked the ones that would be least likely to be replicated and would make more news.
So I think, so as I understand their protocol, they made, I believe, so I think you probably have I'm just going off of sort of what they said in their supplement. I believe they made 157 studies available based on, I think, chronology, and then picked only 100 of those were replicated, so that 157 versus 100.
Within each study,
Oh, yes.
the original authors
Got it.
picked the result they felt like replicating.
Got it. Yes. Okay, this is interesting because I know in the write-up they said that the default was picking the final thing in each study, but there were some deviations. I think in 84 of them.
Enormous deviation.
Oh, you thought there were,
I mean,
interesting.
You have to look at it. Unfortunately, you have to get way into the psychology.
Yeah.
There was considerable variation.
Hmm.
And also the replications were not faithful to the original study.
Yes. So that point
I'm
we
sure the economists were better because they weren't actually redoing the experiment. Or they were.
They were.
Okay.
Yeah, I mean, so in that, so we cut the data a bit to sort of try to get a little bit at that critique. Basically, we redo the analysis, limiting attention to the subset of approved replications where they got approval from the initial authors. I mean, it doesn't fully address it.
And what's the selection on the outcome?
Yeah, no, absolutely. I entirely take the point, but it's trying. I very much agree, and it's a problem with replications, and we're trying to move in that direction. But I agree, it's not perfect. So, right, I mean, first, maybe we don't think we always have great replications, and second, in many cases, we have no replications at all. Right, so this replication approach isn't always applicable. So we also think about a second approach based on meta studies. Right, the idea here is we assume that the estimates X star, right, and note that these are now the unscaled estimates, which comes back to our conversation earlier, are going to be normally distributed, centered at theta star, with variance sigma star squared. The key assumption that we're going to make in this setting is that, again, at least conditional on some set of variables, sigma star is independent of theta star in the population of latent studies. Right? This is a quite strong assumption, but is actually implicit in a lot of the meta-studies literature. Moreover, something that's nice about our replication settings is that we can estimate the model both ways. And when we do that, we get broadly similar results, which doesn't say that this is a great assumption, but at least says that in the cases where we have 2 ways to estimate the model, we get similar answers. So the next thing I want to do is just walk through the intuition for the identification argument for each of these approaches. And before giving you sort of the formal results, I want to just kind of sketch the intuition in a picture. So first, let's think about the replication approach. So here we're looking at the joint distribution of the original and replication estimates in simulated data, so I see all the original estimates. Where here we've colored the studies where the original estimate is insignificantly different from 0 at the 5% level in gray, and colored the ones that are significantly different from 0 at the 5% level in blue. Right, moving from the left panel to the right panel, we're thinking about the same publication rule I discussed in the simple example before, where we drop 90% of the statistically insignificant estimates. Right, so we just drop 90% of the gray dots. Looking at the left panel, the key point to note is that this distribution is symmetric around the 45-degree line. Right, so if I flip the axes, the joint distribution doesn't change. Once I move to the distribution of published studies, though, we see that's no longer the case. And in particular, if we compare region A, which are studies where the original is significant, but the replication is insignificant, and region B, where the original is insignificant and the replication is significant, right, we see that in the population of latent studies, those two events arise with equal probability. By contrast, in the population of published studies, we see a lot more studies in region A than in region B. And the intuition for our identification approach is that it's that asymmetry which will allow us to back out the conditional publication probability P. Oh, wrong way.
You know, I have another suggestion.
Yeah.
These are all of these are just, you know, like ways to tweak the model to see what happens.
Yeah.
So I can imagine that the original author would push harder than the replication author to get a result.
Yeah.
But I think it is also true that the replication author would have a much bigger sigma squared than the original author.
Mhm.
Because the replication author, I mean, if you look in people's file drawers, what's actually there is a whole bunch of screwed up experiments. Like you tried it one way and you switched X and Y and you asked people the wrong questions. That's what most of research is, right?
Yeah.
And by the end of it, if everything's right, then they finally have figured it out.
Mm-hmm.
Somebody who comes along after the original author spent 4 or 5 years working on something and
Yeah.
just tries to follow the results that were written in the paper, which probably don't include everything.
Yeah.
Undoubtedly, it's more variable.
No, absolutely.
And there's some incentive, of course, for the sign or the significance to flip.
Yeah.
But even aside from that, which
Yeah.
is maybe an evil intent, with no evil intent, you would expect a bigger variance.
Yeah.
Right. And
Absolutely.
So you might see what happens if you do that.
Yeah, so that makes a ton of sense. I think we thought a bit about this issue, and one thing that comes up there is basically, so when you say a larger sigma squared, what you have in mind, correct me if I'm wrong, what you have in mind is basically there's some, right, the parameter estimate and it's not that the reported standard error is necessarily larger, but it's that the parameter might be slightly different because you implemented the study a little differently, so you're estimating something a little different.
Either that, or
Okay.
the parameter is exact, or even if the parameter is exactly the same, you're just drawing the estimate. The estimator is more inefficient because of a whole bunch of decisions
Got it.
that are basically randomly chosen.
Got it. So if that's captured in the standard error, that's excluded in the baseline setup, but the thing we actually use for estimation ensures that if that's included in the standard error, then it's fine. It'll be taken care of.
Yeah, but it wouldn't be because
but
you're
yeah.
conditioning on, you know, whether the sun's coming in this way or whether you let people in this way or whether people are coming from Harvard Square or they're undergraduates.
Right, yeah.
You know, how they're dressed, what time, what the person that meets them, all these things are just, you know, the original authors, some of them they would have locked down as controlled variation. And in a replication study, the original author might not have been, we certainly wouldn't be able to specify all of those things. And the replication author they're only going to do it once. The original author probably did it 50 times.
Absolutely.
Right, so it's just have a bigger variation. It's just a more inefficient estimator in a sense.
Yeah, but more inefficient, but in a way that doesn't show up in the standard error. Basically, is the problem.
So, 'cause you're conditioning on it.
Yeah. So then I think for us, I think if it shows up in the standard error, we can take care of it. If it doesn't, then it sort of becomes this, the replication isn't there's some extra noise in the replication. We don't know how much. One thing we thought a little bit about there is basically if we had 2 replication studies, right, then you could imagine basically compare between replication studies, how similar is the answer, how much of that is actually explained by the standard error and how much residual variation is there, and then try and use that to get some measurement of that thing, which you could then incorporate into this type of correction. That's not something we've done though.
Another response to that though is even if the standard errors are too small relative to the true variability, that doesn't necessarily mean that the symmetry is broken of the true underlying parameters, right? So you could have a misreporting of standard errors in a way that comes from all this tweaking around,
Right.
but flipping the 2 estimates wouldn't necessarily break symmetry.
Right.
That's also
It just may change your estimates somewhat.
I mean, like the abstract identification argument would still go through, I think.
I mean, I agree, it would still be asymmetric or whatever, but if the replication were much more variable, even if it's identified, wouldn't you get, I mean, you get different estimates? I'm not exactly sure what I'm
Again,
talking about.
is this scaled by the standard error here? It is.
Yeah, I mean,
So then you
yeah.
would have a change in the test statistic if in the replication study you had greater variability because of the
Yeah.
decision making.
Right. I mean, basically, so the issue is what the results I'll show in a minute. Basically, we show that if, right, basically, if the two studies have different standard errors, right, but the standard errors are right, that's fine, right?
Mhm.
Basically, our identification results extend to that case. The sort of exact symmetry argument we've been using doesn't hold there, but basically, you can extend the logic and it's fine. I think this case with residual, sort of unaccounted for residual variability is, I think it would depend on sort of exactly how that showed up. But it's a very interesting question. We should think more about it. Thank you. So to formally state our identification result here, I'm going to just take the model we had before, right, where we have a true effect theta drawn from a distribution mu, estimate conditional on theta follows f of x star given theta star, and then a publication probability which conditional on the estimate and the true effect depends only on the estimate. And we'll just augment that by adding a replication draw, right, where the assumption here is that conditional on the original estimate, the publication decision, and the true effect, the replication draw is drawn from the same distribution as the original estimate. Right, so this just corresponds to what I was saying before, right? We have a replication implementing the same protocol. Again, we only observed published studies, and for published studies, the true effect is theta j, and we observe the original estimate and the replication estimate. So in this setting, if the support of the original and replication estimates is of the form A cross A, then the publication probability P is identified on this support up to scale. And I'm not going to go through the full argument for this, but the intuition is pretty straightforward. Right? If you think of the marginal density of the original and replication estimates in this setting, right, without publication bias, right, it would just be given by the joint density conditional on the true effect theta, integrating over the true effect theta. The only effect of publication bias is then just to rescale this by a publication probability that depends on the true effect and a constant which ensures that it integrates to 1. Right? But if you then think about any pair of values, A and B, such that the probability of publication conditional on A is strictly positive, if I look at the ratio of the joint density at BA relative to the joint density at AB, right, that recovers the ratio PB over PA, right, which shows that we can immediately recover the publication probability up to scale. Now, like I was suggesting earlier, when we come to try and apply this in practice, there are a few complications we need to deal with. The first is that while we do assume that the replication experiments estimate the same effect theta, they often have a different sample size. Right? Consequently, there's a different variance potentially in the original and replication estimates, which breaks the sort of very sharp symmetry property I was relying on here. Moreover, the replication sample sizes are often determined based on power calculations using the original estimate, right? In the sense that the replication sample size is chosen to ensure a particular level of power to detect the effect estimated in the original study. Despite this, we show that if we add the assumption that X is normally distributed, then the conditional publication probability P is still identified up to scale. And moreover, this assumption of normal errors allows us to identify the distribution mu of true effects as well. So that was the identification result for the case with replication studies. Next, I'm going to talk about the identification results for the case with meta-studies. And again, I just want to start by talking through this with a picture. So on the left panel, I again have the picture for the population of latent studies. On the horizontal axis, I have the estimate X star, and on the vertical axis, I have the standard error sigma star. The gray cone here denotes the boundary for the region of statistical significance at the 5% level. Right? Again, gray dots correspond to studies which don't reject 0 at the 5% level. Blue dots do reject 0 at the 5% level. moving from the left to the right panel, we see that we're just dropping 90% of the insignificant studies corresponding to the same publication rule I discussed earlier. Now, the intuition for the identification argument in this case is that if we look at the left panel, that is in the population of latent studies, the independence assumption we made between the standard error and the true effect ensures that if we consider the distribution of studies conditional on standard error equal to some level, say B, right, and some other level, say A, right, the distribution of estimates conditional on B is just equal to the distribution of estimates conditional on A plus noise. By contrast, when we move over to the right panel of published studies, we see that's no longer the case. And in particular, if we take the distribution here and add noise, we don't end up with the distribution at B. And there's missing mass inside of this cone. Right? There are in some sense too few statistically insignificant studies relative to what we would get if we just added noise. Right? Again, the intuition here is it's that the deviation from that prediction which is going to allow us to identify the conditional publication probability. So to formally discuss this result, let me introduce the model. Right, so here we'll think about there's a standard error, sigma I star, which is drawn from some distribution mu. The true effect theta I star is then drawn independently from some distribution mu theta, right, where this is the crucial independence assumption I mentioned earlier. The estimate xi star is then normally distributed, centered at theta I star with variance sigma I star squared. And the publication probability is assumed to depend only on the z statistic, that is the ratio of the original estimate and the standard error. As before, we observe only published studies, and for those studies, we observe the estimate and the standard error. Finally, I'll denote latent z statistics by z star and published z statistics by z. Now, in this setting, provided the support of the standard error sigma contains a neighborhood of some point, right? Basically, it's not just a collection of isolated points. Then the publication probability P is again identified up to scale. The argument here is somewhat more involved, so I'm not going to go through it in detail, but just to sort of sketch roughly where, what in the data are we using to identify this. Note that the conditional density of z given sigma is of this form in this setting. If we take the ratio of those conditional densities at a given z for two different values sigma, it's then of this form, right, where this pz cancels out. Now, if you look at this, right, the first term here depends on sigma but not on z, so only the second term depends on z. So what we do is we take the log of this and then differentiate to get an object that depends on z alone. Right? Using that object, we're able to show that we can identify the distribution mu of true effects. And once we have the distribution mu of true effects, we can recover P from this first equation. So before I move on, any questions about that?
You just say, interpret this in terms of the figure you showed earlier, which was about slices of the distribution of meta-studies?
Absolutely, right? So essentially what this is saying is right, so what is this comparison doing? Right, this comparison is fixing the z statistic and varying the standard error, right? In this picture, that corresponds to moving out along one of the rays, right? Basically, so the z statistic is constant along rays out of this point 0, right? And so basically what we're doing is we're moving along those rays and sort of looking at how the density varies along those rays, and that's what's going to allow us to recover the publication probability P. Does that make sense?
Yes.
Great. Any other questions? Okay, so next I'll talk about bias-corrected inference. So once we know the conditional publication probability P, we can correct inference for selection. In particular, the density of published X given theta is of this form, right? Where basically the effect of selective publication is to take the distribution in the population of latent studies and reweight it by the publication probability P. We then have to divide through by a function of theta to ensure that this integrates to 1 in terms of X. And we'll denote the corresponding cumulative distribution function by capital F of X given theta. Now, we're interested in bias and in the coverage of confidence sets. Right? Previously, we were thinking about the parameter theta as having some distribution in the population of latent studies. But here, we're focused on a standard frequentist analysis. So we think about trying to derive results which condition on the true effect theta, right? So thinking about 4 studies where the true effect is 1, 2, and so on. Now, define theta hat alpha of x in this way, right? So this is the value theta such that if I evaluate the CDF at the observed data and theta, it's equal to alpha.
One step
Yep.
back again on the interpretation of this. I mean, if I'm
Yeah.
understanding correctly, what you're going to be getting out is the correct distribution of theta, which might be interesting in some sense from the perspective of sociology of science. What is the underlying distribution of the z statistics? But for any given substantive area, you're not giving me effect sizes.
No, that's actually not what we're aiming
Okay.
at. What we're aiming at is basically we want to say, so right, think back to this treatment effect example I started with at the beginning, right? So we've got a lot of different studies trying to estimate the effects of different treatments. Things that are significant are 10 times more likely to be published. Things that reject 0 at the 5% level are 10 times more likely to be published than those that don't. And what we are trying to do here is basically say, we know that the published confidence interval for a given study does not cover the true effect with the right probability. And what we're trying to do is to give you a confidence interval that does cover the true effect for each individual study. Exactly. Yeah, so that's why, effectively, that's really why we're conditioning on theta here, is we want to say, if the true effect is in this study is 1, I want to cover it with 95%. If it's 0, I want to cover it with 95%, and so on. Yeah. The other object, the distribution of true effects is also interesting, but we agree that often, we care about the parameters in individual studies, and so we're trying to get at those as well. And so the way that we're going to do that, right, is we define theta hat alpha in this way. Intuitively, what is this theta hat alpha doing? Right, this theta hat alpha is the value of theta such that the observed data x lies at the alpha quantile of the corresponding distribution. Right, so basically, in some sense, we're inverting the cumulative distribution function in the parameter theta to try and back out the value of theta such that the observed data lies at the alpha quantile. And once you do this, using monotonicity properties of the CDF, you can show that the probability that that theta hat alpha lies below the true value theta, conditional on theta, is exactly equal to alpha for all theta. That is, the alpha quantile of this estimator is always equal to the true parameter value theta. Right, so for example, by considering theta hat of 1/2, we've constructed a median unbiased estimator, right, which is equal probability of over and underestimating the true effect, correcting for publication bias. Likewise, to construct an equal-tailed 1 minus alpha confidence interval, we can look at the interval theta hat alpha over 2 and theta hat 1 minus alpha over 2, which you can show is guaranteed to cover the true parameter value with probability 1 minus alpha. So to see what this looks like in practice, let's go back to this treatment effect example I discussed before, right, where significant results are 10 times more likely to be published than our insignificant results. Right, when we do that, this is what our corrections look like. So on the horizontal axis here, I have the published estimate x. On the vertical axis, I have theta. This gray line corresponds to the usual estimator, right, which just if the published estimate is 1, the estimate is 1. Right, the upper and lower gray lines are the usual upper and lower 95% confidence bounds. The thick blue line is our median unbiased estimator. Right, so for example, this says that if the published estimate is 1, our median unbiased estimate in this setting is about 0.4. If the published estimate is 2, our median unbiased estimate is about 0.7. Likewise, the thin blue lines are our the equal-tailed confidence bounds constructed in the way I just described. So we see that when the true effect is close to 0, correcting for publication bias in this context actually gives us a tighter confidence interval than the usual one. Right? But as we move out here, it's shifted downwards relative to the usual one, and then is wider over a range a bit above 1.96. So those are the results on corrected inference. Unless there are any questions about what I've covered so far, next I'm going to move on to the applications. Great. Yep.
Is it intuitive that there's going to be that change in concavity when you move on certain values?
Not to me, anyway. It's basically coming out of, right, in some sense, because this estimator theta hat alpha is the inverse of the CDF in the second argument, right? What it's coming out of is basically the CDF itself ends up having a kink, basically due to the publication bias, because the density drops discontinuously when you cross the publication threshold in this model, right? And so sort of very heuristically speaking, I think that's what's inducing the kinks in the estimator, right? But I sort of don't have, at least I don't think we have like a great, well fleshed out intuition for like the changes in concavity. That's a great question, but it's also, in some sense, it's also going to be specific to what model you think of for this publication probability P, right? You could get many different things. Any other questions? Okay, so next onto the applications. So our first application is to replications of lab experiments in economics. And here we're drawing data from Kammerer et al. 2016. So the sample here consists of all 18 between subject laboratory experiment papers published in the American Economic Review and the Quarterly Journal of Economics, which are two top journals in economics, between 2011 and 2014. So on the next slide, I'm just going to plot the data, where I'm plotting the Z statistic in the original study, as well as the estimate in the replication study normalized by the standard error in the original study. The reason I'm doing this, rather than just giving you the Z statistics in both studies, is to put these two things on the same scale, because the standard errors differ across the original and replication. The initial estimates are also normalized to be positive. Right, so this is what the results look like here. We see that out of the 18 studies, there are only 2 that are insignificant at the 5% level and 16 that are significant. And it looks plausible that there's some action in the density around the usual 1.96 cutoff here. So when we estimate the model here, we assume that theta star is normally distributed with mean 0 and variance tau squared, and we specify a simple form for the publication probability P. In particular, just like in the running example I've been using, we assume the publication probability for insignificant results at the 5% level is beta P, and the publication probability for significant results is 1. Note that because this publication probability is only identified up to scale, this assumption that the publication probability is 1 for significant results is just a scale normalization. Right, so the free parameter here is just beta P. When we estimate this model, our point estimate is actually 0.1. So we estimate that in these data, results that are significant at the 5% level are about 10% as likely to be published as are significant results. Right? So this actually corresponds to the value I've been using in the running example. So one thing we can do with these estimates is if we sort of take the point estimates at face value, we can revisit the results of these 18 studies. Right? So that's what we're doing here. For each of these studies, we have the original estimate and confidence interval in blue and our adjusted estimate and confidence interval in black. Right? While only 2 of the original confidence intervals cover 0, right, 10 of the adjusted confidence intervals do. Right? So it looks like correcting for the estimated degree of selection substantially shifts the distributions of results towards 0. Right? Another way to look at these adjustments, here I'm plotting the original estimates in blue, the adjusted estimates in black, and the replication estimates in gray. Right, and what we see here is it looks like our adjusted estimates are doing at least a reasonably good job of tracking the replication estimates in this application. So as I suggested earlier, while we have replication data here, we can also estimate the model in this context using our meta-study approach, which just focuses on the estimates and standard errors from the original study. All right, so here I'm just plotting the data in the same way that we did earlier for the meta-study approach. Right, again, we see these 2 statistically insignificant results. The others are significant. Right, we estimate the model, again allowing the possibility of a discontinuity in the publication probability at the cutoff for significance at the 5% level. And when we do that, we get beta P equal to 0.45. Because the normalization of the estimates is different, the parameters tau, tilde, and tau aren't directly comparable, so the comparable parameters are just the beta P's. And when we look at those, we see that, I mean, they are somewhat different, but I think it's fair to say that they are roughly similar across these two approaches in this setting. So those were the results for lab experiments in economics. The next set of results are for lab experiments in psychology. So here we use data from the Open Science Collaboration 2015, who replicated 100 out of the 488 articles published in 2008 in Psychological Science, the Journal of Personality and Social Psychology, and the Journal of Experimental Psychology, Learning, Memory, and Cognition. Here, we focus on the subset of 73 studies which use approximately normal statistics, by which I mean Z statistics, T statistics, chi-squared statistics, F statistics, things that we can think of as at least close to testing based on Z statistics. Now, there are some critiques of this study by Gilbert et al. 2016, including some misinterpretation of the results in terms of the rate of replicability, and that not all of the replication protocols were endorsed by the original authors, right? As I was suggesting earlier, to try and get towards this critique, although I recognize it doesn't fully address it, we rerun the estimators on the subset of approved replications. Right? When we do that, we find that the results are broadly similar, although they do suggest somewhat less selection, suggesting that either the authors who approved it, there may have been less selection in that population, or perhaps that the replications were more faithful to the original studies. So here I'm beginning by again just plotting the joint distribution of the original and replication estimates. We see that again, it looks like there's a fair number of studies close to this boundary of statistical significance. Here, since we have a bit more data, we estimate a slightly more flexible model. And in particular, we allow discontinuities in the publication probability depending on whether the study is insignificant at the 10% level, significant between the 5 and 10% levels, and significant at the 5% level. So again, these publication probabilities are measured relative to publication probabilities conditional on significance at the 5% level. When we do that, we estimate that results which are insignificant at the 10% level are about 2% as likely to be published as a result significant at the 5% level. Results significant at the 5% level are in turn over 3 times as likely to be published as results significant at the 10% level, but not the 5% level. Right, so as in the economics application, we find substantial evidence of a selection on statistical significance here. Again, as in the economics application, we can also estimate the model in this setting using our meta-study approach. And when we do that, we again get broadly similar estimates. As before, the parameters tau aren't comparable, so the ones to compare are the beta parameters. And we see that, certainly up to sampling variability, the estimates we get in these two settings are quite similar. Now, these are the results I mentioned before to address the critique of Gilbert et al., right? That some of the replications may not have been very faithful to the original studies. Right, so here we limit attention to the subsample of 51 studies where the authors of the original studies approved the replication protocols used by the replicators in advance of the replication. Right, when we do this, we get a broadly similar pattern of estimates to what we did in the original studies, though the beta p parameters are systematically a bit larger. Right, again, this is consistent with either there being less selection in this population or potentially with the replications being higher quality, more faithful replications. So the next application is to a meta-study on the effect of minimum wages and employment in the economics literature. So in particular, we're drawing data from Wolfson and Bellman 2015. They look at studies which estimate the elasticity of employment with respect to changes in the minimum wage. Where here, the normalization of the estimates is that x greater than 0 corresponds to a negative employment effect. Now, the sample consists of 1,000 estimates from 37 studies using US data that were circulated after 2000, either as articles in journals or as working papers. So a complication here is that for some of these studies, there's more than one estimate per study. Right, so here I'm plotting the data. Because there are 1,000 estimates, it's kind of hard to see any patterns here. But when we turn to the model, here, since we have more data, again, I'm going to allow a more flexible specification. In particular, since the sign of the estimate seems like it could plausibly matter in this setting, right? We might treat studies which estimate that increasing the minimum wage increases employment differently from studies that estimate that increasing the minimum wage decreases employment. We allow the publication probability to depend both on the sign of the estimate and on whether a two-sided z-test rejects 0. When we do that, these are the estimates we get. So the interpretation of this is that an estimate which says that increasing the minimum wage, a significant estimate which finds that increasing the minimum wage increases employment, right, is about 23% is likely to get published as a significant estimate which finds that increasing the minimum wage decreases employment. And the pattern of estimates is monotonically increasing as we go from one end to the other, right? So basically, the more you find, the more that, according to these estimates, the more that a study finds a negative effect of the minimum wage on employment, the more likely it is to be published. So finally, the last application is to data from Croak et al. 2016. They follow the procedures outlined in the Cochrane Handbook of Systematic Reviews of Interventions and collect data on randomized controlled trials of deworming that include child body weight as an outcome. They end up with a sample of 22 estimates from 20 studies. Right here, we're plotting just plotting the data. And because we don't have a whole lot of data here, we allow the publication probability just to depend on significance at the 5% level. When we do that, we get a point estimate which suggests that insignificant estimates are actually more likely to be published in this setting than our significant estimates, though the standard error is quite large, so the results here are quite noisy. Moreover, in this setting, the results are actually very sensitive to the particular specification we use. For example, if instead of allowing selection to depend on whether you're significant at the 5% level or not, we allow selection to depend on the sign of the estimate. Right? Basically, do you estimate that deworming increases child body weight or decreases child body weight? We find strong evidence of selection on that. Basically, studies which estimate that deworming is likely to increase child body weight are more likely to be published than those that estimate it decreases them. All of which is to say that basically the results in this application are pretty fragile, so I would hesitate to interpret them too much. So that's actually what I wanted to cover, so let me wrap up. So selectivity in the publication process is a potentially serious problem for statistical inference. To deal with this, we first non-parametrically identify the form of selectivity. Using replication studies, we use the idea that the original and replication estimates would be symmetrically distributed absent selectivity. Likewise, using meta-studies, we use the fact that under an independence assumption, the distribution of high variance estimates would just be a noisier version of the distribution of low variance estimates. Again, deviations from that prediction will allow us to identify the form of selectivity. Now, once the form of selectivity is known, we can derive easy to implement corrections, in particular median unbiased estimators and equal-tailed confidence sets with correct coverage. Applying our results, we find substantial evidence of selectivity on statistical significance in experimental economics and psychology, selectivity towards negative employment effects in the minimum wage literature, and selectivity towards insignificant effects in the deworming literature, though the estimate is very noisy and the results are quite fragile. So, thank you very much.
You have time for a few questions?
Does your estimation procedure for P depend on how it's parameterized in that? It's like a threshold function.
Yeah, absolutely. So so in some sense, our identification results are non-parametric, right? So our identification results allow both the distribution of theta and the publication probability to be fully non-parametric, right? But when we come to the applications, we're specifying these parametric models and then fitting it by maximum likelihood. So it very much does depend on the specification we're choosing. We could certainly get away from the parametric assumption on this. With finite data, getting away from some assumption on P seems tough, though it's definitely worth thinking about. Any other questions?
I'm just wondering just what sorts of work ends up getting included in the same meta-study or ends up counting as a replication. I think from the question about the protocol and asking the original researcher to approve or disapprove the protocol,
Yeah.
we're talking about a case where work is being overtly undertaken as replication of another particular work, right?
Yes, absolutely.
And is it the case that those 18 economics papers and 488 psychology papers that were published, none of those 18 published were overtly replications of any of the other 18,
Yes,
but there was a cooperative effort
exactly.
where people volunteered their time to
Yes.
try to replicate. The recruiters found
Exactly.
someone who would try to replicate each of the 18.
Precisely.
So you're looking at a population, in the case of this meta study for experimental, you're looking at a population of pairs of studies where they were overtly
Yes,
replicating the published one.
absolutely. Yeah.
Informally, certainly an economist talking to students in class would say
Yeah.
something like, well, this couldn't be replicated with New Hampshire data from the 1970s.
Yeah.
But when we actually look at the minimum wage stuff, are we
Yeah.
basically, the meta studies typically counting, how do they decide what's a minimum wage study? Are
Yeah.
we counting every work that has been published or circulated in a working paper,
Yeah.
but maybe not class projects that my undergraduates turned in
Right,
for a
exactly.
semester course? But
Yes.
the threshold, I mean, I'm wondering, how do you even find the population of all studies
Yeah. No.
of minimum wage effects,
It-
of working papers on minimum wage effects? Is it actually including things like someone did something clever with longitudinal data for the entire 20th century
Mhm.
and circulated it as a working paper in 2011? That's
Yeah.
going to be in there, right?
I
And
believe.
if someone studies
Yeah.
the shipping industry during World War II,
Mm-hmm.
the fact that they're doing the research in 2011 to 2014 means that it's going to be in the study
It should
as
be
one
in.
of those dots.
Yeah. So in this minimum. So you're thinking of this minimum wage context.
Well, I
Yeah.
actually, I don't know anything about the whole meta study
Oh,
business.
okay.
so I'm
Yeah. Yeah.
wondering-
Yeah.
I was using this, really, this is only an example.
Mhm.
I mean,
Yeah. Yeah.
um, is there an ongoing effort to compile databases of
Yeah.
all minimum wage studies that have ever been not only published but circulated?
Right. I
And-
mean, in some sense, I think that's
and
the.
you're coming in
Exactly.
to look at a field where the people working in the field, they've organized this effort for some years,
Precisely.
and they're basically giving you
Precisely.
a data set which is their compilation of all of the known work on minimum wage employment effects?
Precisely. Yeah, that's exactly right. So, I mean, it's depending on which of the, right, so for the different applications, right, so the minimum wage application, Wolfson and Bellman compiled this data and were kind enough to share it with us, right? And they exactly went through that exercise of like trying to find everything they could that fit their criteria. For this deworming study, it's very similar actually, right? So there's actually in the meta-study literature, my understanding is there's some set, there's disputes about this, but there's some arguments about what are best practices for doing a meta-study, right? Sort of how should you set the parameters for inclusion? Once you set those parameters, how can you make sure that you've exhausted the universe of all studies fitting those criteria, and so on, right? So for example, this Cochrane Handbook for Systematic Reviews of Interventions is primarily medically oriented and is exactly basically trying to set up those sorts of criteria. And so that's what this meta study by Crocodile did, is they went out and tried to find all the studies meeting those criteria and build that data set. And then we're just piggybacking off of that.
Maybe more abstractly also, it's in a way a matter of how to interpret the distribution mu and the function p. It's really the underlying population of studies that could potentially end up in the meta study and the selection to be in the meta study. So in a way, the function p includes then not only the publication decision, but also the inclusion decision in the meta study.
In a more complicated model, or
This
is
is just like
we should
taking
think of
our
it as being
model,
built
but
in. We should
interpreting
think of
it.
that as being incorporated in.
Exactly. It's sort of implicit. It's
Yeah.
implicit in our model. Yeah, exactly.
And to the extent that we're actually interested in publication as opposed to the meta study, then the hope would be that the meta study is systematic about what they include. But
I mean, yes, exactly. Sort of all of this is.
Yeah.
Yeah.
Yeah, I was wondering how your work relates to some of the more ancient stuff from the 1970s and 80s. So, there's this well-known paper by Bob Rosenthal
Hmm.
on file drawer problem.
Yeah. Absolutely.
And that, I think it was published sometime in the 70s.
Yeah.
And then there was a flurry of activity that was far more technical in the early 80s. viewing this as a missing data problem.
Yeah,
Yeah,
absolutely.
And which is the studies that get published, there's a selection, this underlying thing is normal or whatever you want it to be. And the ones that are not published are missing, they're sitting in file drawers. And so it's actually with the creation of EM algorithm in '77, there was a whole flurry of activities viewing it that way. And there seemed to be no connection here to their work at all. And I sort of think that the connection is actually very tight. I'm wondering whether you actually looked in the literature of the 80s to see whether you're actually duplicating stuff that's been done.
We
The
did,
paper
yeah.
we do a fairly systematic review of various methods, and I guess Rosenthal is basically worst case bounds, if I remember correctly.
It's
It's basically doing worst case bounds about the fine drawer.
right.
Making
You know,
worst
how
case-
many
and
unpublished
then-
studies would there have to be to make this current study insignificant? Yeah.
Exactly, and then like a big one are these meta regressions, which are kind of like a parametric analog of our meta studies approach. So in a way, we're building off that for the meta studies approach. And then there's a bunch of people estimating basically parametric models of selection that are somewhat related to what we are doing, but only identified parametrically. So I guess in a way, we're coming in by adding identification results and kind of being explicit about the identifying variation as opposed to just identifying a functional form there. And then what else was there?
There was also a bunch of
Yeah.
stuff
Because there's the
by
discontinuities in
Larry
published p-values
Hedges when he was at
and
the
Yeah.
University of Chicago.
So actually the hedges, I mean, so the parametric specifications, yeah, so I omitted I wasn't sure how much time I would have, so I omitted the literature review slide, but I mean, we discuss what we're doing is absolutely related to literature. And for example, the parametric model we're estimating here is very closely related to hedges,
I don't
actually.
see
I mean,
why you
it's,
call it non-parametric.
Yeah.
I see a little big N up there.
right, no, exactly. So this, I
see
mean,
parameters.
right, I mean,
I
this
don't
is,
quite see that as non-parametric.
right, no, so this is very much, I mean, this is very much of the same
Yeah,
type
yeah,
as
I-
hedges
I-
estimated, right? And
It
so I
looks like
think
it's almost
the,
identical.
it is, yeah.
Okay.
Well, so right, I mean, the replication stuff is, the replication model is different. And I think, like Max was saying, right, another contribution is basically, we've looked fairly hard in this literature, and as far as we can tell, all the identification arguments about the conditional publication probability out there in the literature that we were able to find were parametric, right? And so basically saying that actually, you know, the variation in the data is enough to let you recover this thing without parametric assumptions, right, I think is
So
a
you're
contribution.
You're
that
saying
we've
you're not making parametric assumptions?
in the application, we absolutely are, right? When
So
we
what's non-parametric about that?
come back here, right? So for
Presumably
example,
normal?
this result, right? So here we assume that the x is normal, but for example, the distribution of the parameter theta, the distribution of sigma, the publication probability p, all of those are fully non-parametric, right? So those are identified without having to add these additional assumptions.
Fully identified, see,
Up to scale, I mean, p is identified up to scale.
It's kind of the equivalent of having a Heckman selection model without an instrument would be the old version of the selection models, and Forrest is saying you really need an instrument, and just like by analogy, or you need exogenous variation to identify it.
The phrase non-parametric, I guess, is in the eye of the beholder to some extent.
There's non-parametric identification, and then there's estimation in a finite sample.
Yeah, so you're avoiding some specification on the prior distribution or something like that.
Well, it's not really a prior distribution, it's a
I know you're not using, but it basically is. It's a distribution of a parameter in a population.
But it's an identified distribution, it's an empirical object.
You can argue about that. Yeah, that's a point of, that's what I'm saying. What does it mean to be non-parametric? That's sort of a definitional problem.
Sure, but like if you can have a randomized experiment, and then you can say the effect is not parametrically identified if you fit a linear model to that, and your estimation is parametric, but the identification of the causal effect is not parametric if you have random.
And the estimation is, I mean, randomized experiments are a special case because there are no parameters. That's non-parametric. I agree. That's legitimately called non-parametric. There are no parameters.
Okay, and the claim would be this is kind of an equivalent situation.
Only based on the randomization? I don't think so.
So for example, so this may speak partly, so for example, based on our results, that we haven't implemented it yet, although perhaps we should, both here and in all our applications actually, we could, I haven't seen a way to get away, sort of a way to implement a sort of traditionally non-parametric looking estimation algorithm in P, but we could estimate all of these applications without assuming any distribution on theta, for example, right? So we could leave that fully flexible. If we had an infinite amount of data, we could also be fully flexible about P, but with a finite amount of data, we haven't seen a way to do that yet. So that may come partly towards addressing that concern.
But the constraint on selecting that is sample size, not identifiability.
We're using the terminology slightly differently, so. It's probably boring to everybody else, so.
Okay, thank you so much.
Thank you all very much.